Alright, so today I'm going to explain the laws of thermodynamics. Now, the first law states that energy can neither be created nor destroyed. So the change in the energy of the universe, which we'll write as delta U, this little triangle thing here being delta, so the change in the energy of the universe has to equal 0. Energy can't create it, can't destroy it. Energy can, however, be transferred to different forms. So, for example, let's say you've got a log here, and you set fire to it, and so now it's burning. Well, it may seem like energy is being created because you're all warm now. However, what you're actually doing is you're converting the stored chemical energy inside the log into thermal and light and even a little bit of sound energy. So energy can't be created or destroyed, only transferred. To explain the second law of thermodynamics, I need to introduce a couple of dice. So, we've got this die here, just a normal, ordinary die, 6 possible outcomes, 1, 2, 3, 4, 5, or 6. But let's say that, for the purpose of this video, that as humans, we consider 5 to be organized. There's nothing inherently special about it. It's still just as likely to occur as any of the other numbers, a 1 out of 6 probability, but we as humans consider 5, and only 5, to be ordered. Now let's throw in another die. So in this case, the number of possible outputs has increased to 36, actually. However, we still only consider only 5s to be organized. But the probability of this has decreased to 1 out of 36. So, in a sense, we can say that the disorder has increased by increasing the number of possible outputs. And this is what entropy measures. Except that instead of the output being a dice roll, it is one way a collection of particles can arrange its energy, which we refer to as a microstate. So entropy measures the number of possible microstates. This brings us to our second law of thermodynamics, which states that for any given reaction, the entropy of the universe must increase, which we can write as the change in entropy, or delta S, must be greater than 0. Now, there are a couple different ways that entropy can increase, and to explain those, I'm going to bring back our dice. Now, one way is by increasing the amount of energy. This works because the particles now have more ways that the energy can be distributed. So, go back into our log example, when we set it on fire, the reason it'll burn is because energy is released, and thus entropy increases. So it's essentially like going from our 5-sided die to a 20-sided die. There are a lot more possible outputs. However, what about an ice cube? Because at standard room temperature, an ice cube will melt, which is actually a reaction that absorbs energy. Well, this brings us to the second way that entropy can increase, which is by increasing the number of particles. Now, as a solid, water is pretty tightly locked together. There's not a whole lot of movability of the particles. But as a liquid, the particles can just slide past each other. They can be arranged in many more different ways. So, by increasing the number of particles, the energy can be distributed in more ways. It's essentially like adding in another die. The second law of thermodynamics actually has some fairly major implications on the efficiency of machines. One of these has to do with heat, which in science is a measure of how much energy the particles have, and work. Now, the second law indicates that an engine cannot be totally efficient because not all of the heat can be converted to work. To explain this, let's say we have our object here, which we're moving with a force F, a distance d. So, i.e., we're doing work on it. Now, doing this work requires that we move all the particles in one direction, which is very distinctly not random. So the entropy actually decreases. This, of course, can't happen, so some of the energy must be lost as heat. And in doing this, the entropy is increased. So the entropy of the universe is actually increased in total because some energy is lost as heat. Now, another thing to do with machines is that some reactions can actually be reversed. And for this, I'm going to bring back our ice cube example. So it's essentially the same process as up here. We can create a cold environment where the water will freeze. However, doing such requires a large use of energy. So in this cold environment, the entropy decreases. However, again, we have to use a large amount of energy, which causes a lot of heat to be released, which ultimately increases the entropy. So the entropy of the universe, again, increases. Now, this actually brings up a fairly interesting point between the relationship of entropy and temperature. So, we've got our ice cube, and then we've got it as water. Now, for the ice cube to melt, it needs to absorb some energy. However, at 300 Kelvin, absorbing the energy does not create a whole lot of entropy, or actually does not absorb a whole lot of entropy. Not much entropy is lost when this absorbs the energy. However, in creating the more particles with more freedom, a large amount of entropy is created. So, more entropy is created than is lost, and thus entropy increases. Now, in going back, when it freezes, the same amount of entropy is lost as was created when the particles re-solidify. However, now the amount of entropy that is released when they freeze is much larger. So, as the energy is released, it creates much more energy than before. This is because of the colder environment. Releasing more energy into it increases the entropy so much more than when it was warmer. So, thus, temperature actually has a fairly major impact on entropy and which reaction will take place. Now, finally, we have our third law of thermodynamics, which states that at absolute zero, a pure crystalline substance will have no entropy, which we can write that at 0 Kelvin, which is absolute zero, the entropy is 0 for a pure crystalline substance. Now, the reason for this is that at 0 Kelvin, a substance will have minimum energy, which in the case of a pure crystalline solid is no energy. As such, if there is no energy, there is no way to distribute that energy, which means there are no microstates. And if there are no microstates, there is no entropy. But what this law really states is that absolute zero is impossible to reach, because there always has to be some entropy. Now, there is actually a Zeroth Law of Thermodynamics, which, if you ask me, is kind of a stupid name, but it was discovered after the other three laws, yet determined to be more important than all of them, and since they didn't want to rename the other three laws, they went with Zeroth. But nevertheless, it indicates that if one thing is in thermal equilibrium with a second thing, and that second thing is in thermal equilibrium with a third thing, then that third thing will also be in thermal equilibrium with the first thing. Essentially, if A equals B and B equals C, then C will equal A. Now, I should mention that thermal equilibrium is when two items have the same heat, i.e. there is no heat transfer between them. Now, keep in mind that in science, heat is a measure of how much energy the particles have. Now, this law really only becomes important in the mathematical side of thermodynamics, which I'm not going to get into for this video, but it does help to define temperature. But, nevertheless, hope you enjoyed it, hope you learned something, and see ya!